Okay, so let us finish out. Let us continue with the fractional factorize. Okay, then if we have a time, then we continue with the following chapter. Okay. So before the holiday, I have discussed with you all about the last example. Okay, on the fractional factorize, where you try to make use of the 1/2 of the fractional design and then to identify the important factors. Okay, based on the 1/2 of the analysis or the 1/2 of the treatment combination they run. Okay, so this one is the first example you can recall back. Okay, so now we'll go through the second example. So in this example, instead of just the 3 factors alone, then we go through is for the 2 power of 5 minus 1. So minus 1 is referred to they only run for the 1/2 of the treatment combination. Okay, so they consist of the 5 factors here. So the factors considered in this case should be the A, B, C, D, E. So you have a 5 factors here. So should be you have a 2 power of 5 is equal to 32 treatment combination. But because we only run for the 1/2 minus by 1, so therefore you only have this 2 power of 4. So you only run 16 treatment combination. Okay. So in this example, first thing is in the fractional factorial design, you need to know what are the factorial design they consider. So in this case, it's 1/2 of the fractional factorial design. This one is the first thing. The second thing we need to consider is what is your generator you use. Okay, you need to know what is your generator. Okay. After that, you also need to know what is your resolution. Okay, so from the 2 power of 5 minus 1 here, in the following example, we consider the generator will use as high as possible the iteration combination. So we use the generator is A, B, C, D, E. Okay, because the generator later on they will affect your alliance structure. So this one is just a 1/2 of the fractional factorial design. So we use the following generator will be the A, B, C, D, E. Okay. And then after that, we can be write down the alliance structure of them. And then from the alliance structure of them, you will know what is the restoration under this case. What is the restoration for this case? Okay. So we will expect that we have a higher restoration than the alliance structure of the main effect with the main effect, or the main effect with the 2 iteration effect. They do not have this type of the relationship. Okay, so later on we'll go through it. Okay, so for the fractional factorial design, okay, first thing is you have the A, B, C, D, E, and then you consider the generator is equal to A, B, C, D, E. Okay, this is the iteration of the A, B, C, D, E. So what we can consider here is first thing you write down the basic design first. Okay, if you do not want to write in the following form, of course you can list down the full table of the all the plus minus signs for the factor A until the factor E. Then you just run for the 1/2. Okay, based on the sign of the A, B, C, D, E, then you know that just 1/2 of them will run for the positive sign, another 1/2 of them will run for the negative sign. Okay, so you have this thing is the I is equal to A, B, C, D, E. Okay, we use the following defining relation of the here. The A, B, C, D, E is your generator. So the following is a defining relation of here. So the relationship were given by here. So first thing is you just what you need to write is just a basic design where they consist of the 4 factors first. So how to write the 4 factors of the plus minus sign? What you can consider is just write the 1 minus plus minus plus alternate of the sign, and then after that for the factor B you write the 2 negative, 2 positive, and so on. Also the alternate. For the factor C you write the 4 negative, 4 positive also. Then after that the last one, the D, is you write all the 8 negative, 8 positive. So this one is called the basic design here. So to get the last factor of here, what is the plus minus sign here? Because you have defined your defining relationship. Okay, so you have a defining relation of here. Okay, the relation of here. So what you need to do is just a E times I will equal to A, B, C, D, E squared. So the E times I is still the E will equal to A, B, C, D. The E square is equal to the I. So therefore, you get the last one. So the sign of the E will be equal to the all these A, B, C, D, E. The sign is multiplied together, you get the positive sign. Then you list down all the sign. These are the sign of the A, B, C, D, E. So from here, you will know that the first treatment combination you should be run is a treatment combination E, because only E positive. The second treatment combination is a A, so you run the A, okay, and so on. So this one is help you how to form the 1/2 of the fractional design instead of you write down the full table of the plus minus sign, okay. So means that the experimenter only run the following treatment combination. They do not run completely 32. Here is a 2 power of 5. You have a 32 run. They only run half of them. 1/2 of them means that they only run 16 of them. It's from 1 until the 16. So you only run here. So we expect that based on all these 16 of the treatment combination, we can identify the important factors, where the factors should be A, B, C, D. And then if you can identify the iteration, okay, the iteration for all the 2-factor iteration, 3-factor iteration, and so on. Okay, so this one is our objective when we run the fractional factorial design. Okay, so this is the experiment where the experimenter have run. Okay, so now we proceed with the following page will be the here. Okay, so this one is the diagram. It show you that what are the treatment combination they run. The first one, they run the A, they run the B, they run the ABC, and so on. So here, here the point here is they represent in the diagram here to show you that the treatment combination they run. Okay, and you have here is another 4 of them. Okay, plus these 4 of them. Okay, and then and here. So in this analysis, they consist of the 5 factors considered in this study. In manufacturing the process for an integrated circuit will investigate in a 2 power of 5 minus 1 design with the objective to improving the process yield. Okay. So in this study, we use I is equal to A, B, C, D, E. Okay. This one is a defining relation, is this one. And then in this study also, we need to know what is a restoration. But if you can't recognize a restoration for the time being, we go through the allier structure first. Okay. So based on the defining relation here, we can find out what are the allier structure of all these effects. So the first one is A, you multiply on the left hand side A, and then on the right hand side also A, you have a is equal to B, C, D, E. Similarly, for the factor B, you multiply with the I, you get the B. You multiply the B on the right hand side, your B become B squared. So you only have a A, C, D, E. So this one is the second one. And so on. You get the factor C, factor D, and factor E. Then if you multiply, you get the AB will equal to CDE, CDE, and so on. So here are all the possible Allier structures under this this experiment of the 2 power of 5 minus 1 by using the I equal to ABCD as a defining relation. Okay, so if you can recall back, if you have if your mean effect is iterate with the two factor iteration, but over here you can observe that mean effect is never alias with the two factor iteration, but the mean effect is alias with the four factor iteration. The two factor iteration also alias with the three factor iteration. So this one will be the restoration of the four here. Okay, so if you cannot recall back what is a restoration, we can go through the here. This one is a restoration of here. Okay, so in this example, the restoration of 4 is means that the mean effect. Okay, the mean effect is the mean effect. Sorry, on okay, sorry. Okay, later I make the correction there. So you observe that restoration 3 will refer to the mean effect is alias with any mean effect. Okay, it's no mean effect is alias with any mean effect. So therefore, it's not the restoration 3 because the mean effect will alias with two factor. For the restoration 4 is a no mean effect is alias with mean effect or two factor iteration, but the two actor is iterate with each other. But in our case, we do not have a two factor and the two factor here. But our result here is a restoration 5 because the mean effect and the two factor do not interact with each other. But the two factor are alias with the three factor. So this one is what our case here. So in our case here, we should be have a restoration is not 4, it's a restoration is a 5. Sorry. Okay. So in our case here, we should be have a restoration is a 5. Okay. That restoration is 5 it means that the mean the two factor iteration will iterate with the three factor iteration. Okay. So the restoration of the 5 here also you can observe from the all the 5 letters here. Okay. If you have only the single 1/2, you can have a restoration it's just a 5. Okay, it's based on what you have here. See, so here are all the Allier structure. Sometimes you also want to know that whether you have completely the whole thing or not. Of course, you need to write it systematically. A, B, C, D, E. After that, you have A, B, A, C, A, D, A, E, and so on. So if you observe that, because we have 5 factors here, so the mean effect you have 5 of them. Okay, it's A, B, C, D, E. For the two factor iteration, you should be have how many of them? It's actually is a 5C2. You get the 10 of them. So you can calculate out. Here is AB 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Two factor iteration altogether, you should be have a 10 of them. For the three factors iteration, you also have a 5C3 is also 10 of them. So it's a consistently here is 10. You have a 4 factor iteration. Five C4 will equal to 5. So you have a 1, 2, 3, 4, 5. Okay, then of course you have a 5-factor iteration. This one is what you have here. Okay, so altogether you have a 10. Here is a 10. Here is a 10, 20, and then plus a 5, 5 and 5 here. So you have a 30. 30 plus one of them. You have altogether is 32 of the. Here is the effects there. Okay, so this one is to be confirmed that you have completely write down all the iteration effect. Okay, so this one is what we have here. Okay, once we get the layer structure of all these things, okay, then now based on the data set there, we do the analysis. Okay, based on the data set you obtain here, then we do the analysis. So how we want to do the analysis? Of course, we can using the idea of the normal probability plot. We plot the normal probability plot for the effects. So means that we calculate the effect for each one. Okay, you're calculating the effect of the A. In fact, you are calculating the effect A plus the B, C, D, E. Okay, so this one is you are calculating all the effects up. So you can be calculate is the effect is given by the here. Okay, so all the effects will be calculating of here. Of course, you have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You have 15 of them. You're calculating 15 of them. Why only 15 of them? Because you can observe your outlier structure here. You have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You only can have a calculating of the 15 effects. Because calculating the effect of the A and the B, C, D, E, they are combined together. Okay, so all together you have a 15 of the effects here. So how to calculate the effects there? You can be use the plus minus sign from here. Okay, from the data set here. For the effect of the A, you can use a minus of the 8 plus the 9 minus the 34 and so on. You can calculate the contrast of the A. After that, you divide it by the number of the replicate is a 1. Okay, then you divide it by 2 power of sum. Then you will get the effect for the first one. Okay, and so on for the B, C, and the D. Okay, and the E. After that, you have all the layer structure here. Okay, so here are all the effects here. You can go back to try to calculate it out. So from the effects here, this one we can ignore it first. We do not consider this one for the moment. After that, for the next chapter, we'll go through it. After you calculate the effect here, you also can calculate the sum of square, because once you get your contrast, you can calculate the sum of square. So the sum of square will be from here, you can merge it to the sum of square here. Okay, but once you get the effect here, we want to know that which one are the important factors. Okay, so based on the sum of square here, we can be see that nearly about the 1, 2, 3, and the 4. These 4 are contribute a lot, whereas the rest of them is just a 1, 3, and the 0.5 and the 5. It's quite small. Okay, so roughly we can guess these are the here, these 3 and this one, since that they are quite important, the rest of them were quite small. But anyway, we can plot the normal probability plot. So based on the normal probability plot, you can confirm that all the effects here is the A, C, and the B, and the AB are important factor here. Okay, so we can be recall back. These are the 4 factors here, but this one, the A, B, C, and AB is not purely come from the factor effect of the A or the factor of the A alone, because if you refer to the here, if you are calculating the A, it means that you are calculating the A plus the B, C, D, E. You are getting the B is actually the B plus the A, C, D, E. Okay, so you need to do some assumption. Okay. So the main effect here, as I mentioned, the main effect A, B, C, D, and the AB iteration are large. Okay, clearly from the normal probability plot here. So because of the calculating the A, B, C and the A, B is actually calculating of all these things. So what we can do some assumption. Otherwise, you need to run the complete analysis. Now we only run the 1/2. So we expect that based on this 1/2, we can get the information of the important factors. So we can be assumed that, okay, we can similar to the previous one, we assume that the certain higher order iteration are negligible. So this one will be lead you to the, if you have assumed that the 3 factor and the higher order iteration are negligible, that means that this one we can be cancel off, this one we can cancel off. Okay, then this one also we can cancel off. So therefore, we will think that the main contributor will come from the A, B, C, and AB. So therefore, we feel safe in concluding that on the A, B, C, and the AB are important effects. But you need to assume that the high order iteration are negligible. But if you think that the high order iteration are important also, then you do not know the main contribution is come from A or come from the B, C, D, E. Okay, so this one is why when you run the fractional design, then we try to, from the small analysis, we try to make the conclusion in general if possible. So this one will be your example for this part. Okay, then to be confirmed that the factor ABC here, then the analysis of the run the another one here, they they run the A, B, C, and the AB. They confirm that really all these factors are important factors. Okay, so after you can identify the important factors, of course we also need to check the normality plots to make sure that the assumption those of the assumption they fulfill the assumption, or at least they don't deviate very much, where is you can be acceptable. So the first one is a plotting of the normal probability plot to check for the residues, and then of course the second one will be checking for the constant variant. Okay, and then this one is here. Okay, so from the plots here is the results there is still acceptable. So therefore, we can be consider this one is our analysis, is they fulfill the assumption of the normality, the constant variance, and the independent sets. Okay. So because the example here, the example of for this example here, they want to, based on the beginning of the story, they want to objective is want to improving the process yield. Okay, so they want to have the higher process yield. So therefore, over here, these are the 3 factors is considers the A, B, C, and the AB, where the AB will be iteration is also significant. So therefore, we plot the following plot. Of course, the C we no need because the C can be stand alone. So if you plotting the A and the factor A and the B for the iteration here, if you want to get the maximum yield of them, then therefore we should be use the height level of the factor A, so that they can get the maximum the height value of the yield, and then between the B minus and B positive. So of course clearly we can see that the B positive will higher than the B negative. Okay, so therefore in the following scenario we will consider the A at the positive side, the B also at the positive side. Okay, of course the C one you can be draw the graph or you can calculate. The C also can have a positive. Okay, the mean of the C, because the C does not, the factor of the C here, they are stand alone independent. So therefore you just check it out at the low level of the C, what is your mean? At the high level of the C, what is your mean? Then you compare which one will produce the higher mean, then you consider it. So in this example, the C is at the positive side also. So therefore, this one is the level you consider if you want to optimize your yield. then you consider the higher level for the factor A, factor B, and factor C. Okay. So this is an example where we consider for the 5 factors, and then under the 5 factors, we only run for the 1/2 of the treatment combination. Then we can make the conclusion. Okay. So this one is the example here. Then from here we go through the last example under this page, under this the part 1 notes here. Okay. Yeah. So this one is for the first for the part 1 of the lecture notes under the fractional factorial design. You can be seen the following example. Okay. So the next one we will go through the second one. Okay. Also we continue for the fractional factorial design. Okay. So this one in this example, okay, we have considered the example 8.1 before. Example 8.1 I can recall back first before you continue with here. In the example 8.1 here, I just recall back what you have learned before. In the example 8.1, in this example 8.1, we have all together is a 5 factors here. We run is a 1/2 also. So these are the 1/2 of them. Our defining reaction we run is a I equal to ABCD. Okay, we only run for the positive side. So in the following example here, in the example 8.3 here, instead of running for the positive sign, we are running the alternate fraction. So the I is equal to the negative ABCD. Okay, if we run on the negative side, also is possible. Okay, so reconsider example 8.1. We have used a 2 power of 4 minus 1 design and tentatively identified the 3 main factors is a A, C, D. Okay, the important one is here. And then the two large effects associated with the 2 factor iteration are the AC plus a BD and AD plus a BC. Okay, so this one is based on the example 8.1. Okay, based on the example 8.1, these are the things you have identified it, A, C, D, and the AD. Okay, so this one is a conclusion you have ACD and the AD here. Of course, the AC you also can be considered as a large also. Okay, AC will be here. So altogether you have is inside here. Okay. So now if we run the alternate fraction, is on the negative side. So these are the experiment they run in. So if we combine the example 8.1 and 8.3 together, then this one will become the full factorial design. Okay, we run the positive side and then we also run the negative side. So this one will complete your whole analysis. But our idea of the fractional is we only run for the 1/2. Just the either is a positive sign or the alternate fraction. Okay. So in this example, it's actually we want to show that if you run for the together of both of them, where you run under the full factorial design, you can get completely the effects for all the factors. Okay. So this one is a line structure of them. Okay. Against this one, I just show you one of them only. I will equal to negative A, B, C, D. So if you want to get the A, will equal to negative B, C, D. So this one is when you run the alternate fraction. Therefore, you want to write it out, you will write the A prime will equal to the A minus the B, C, D. So this one will go to here. Okay, so similarly for the rest of them, we'll do it. Okay. So for the effect here, you also calculate using the similar way, you get the 24.25 and the rest of them will be the similar way of calculation. Okay. So now you run the 1/2, you run the alternate parts. So if we combine the previous information what we have in the example in the example here, you run the 1/2 here. Okay, I show you here. Yeah, in the example of this one 8.1, you run the positive sign, so you get the first one is 19. 19 is actually A plus a BCD. Okay, but over here you run the negative sign. A prime is A minus by BCD. You get 24.25. So if you total out for the first one and the this part plus the alternate part, then the BCD will cancel off. So your A will be actually is the average value of here. So you will get is 21.63. So the 21.63 is actually getting it from the example here is a 19. Okay, you get the first one is 19 plus the 24.25 divided by 2. So you will get 21.63. Okay. And similarly, if you get the average value of the B prime complement side and the B, then you get the average value, you get the 3.13. And the rest of them, if you want to get the BCD, you get the different. So you will get your effects for all the complete effects you can calculate out. Okay. So in the example 8.3, I just want to show you is you run the complete set. Then you will go back to the full factorial design. Okay. So this one is a single replicate of the 2 power of 4 factorial design. So clearly AC and AD are the iteration are the last effect. So if you get the full factorial design, you also can observe that the last effect will be the AC, AD, and then the D, C, and the A. Okay, so you can plot the normal probability plot of this thing, then they can show you that which one will be important. So clearly that you run the A, C, D, and the AC, you can identify that these are the important factors if you run for the full factorial design. However, if you run for the fraction of them, you also can be identify it. But of course, you need to assume that the high order iteration is not significant over here. Okay, and then over here, the alliance structure of these two, because as I mentioned before, BD, okay, the BD is the D is not the very the B is not significant. So we believe that the contribution of the AC here is come from the really from the AC. Okay, so because here you have a BC here, then we also think that the B is have a less contribution. The main contribution is come from the AD because AD is considered as significant. Okay, but you run the full factorial design, this one is can confirm your what you have think just now. Okay, so this one is an example for the 8 point this example for the 8.3 8.3 here. Okay. So for the, because you have 3 factors there, the 3 factors there, we can reduce it into you have 4 factors there, where the 4 factor, the factor B not significant. So from the 4 factors there, we can reduce into the only the 3 factors analysis, where you have A, B, C here, the A, C, D, with their iteration of the here, we can be list down in the following form. Okay, of course, this one is just represent in the graphical way to show that what are the treatment combination. You have factor A, you have factor C, you have factor D here. So with their treatment combination, we can project it into the 2 power of 3 factorial design. Okay. So this one will be the end for the first section of the fractional factorial design. We only consider the 1/2. Means that we only consider is 2 power of k minus 1. Okay, it's just a 1/2. You run for the 1/2 of the fraction. Okay, so we can be further it reduce the number of the treatment combination we run. So that one will be go to the, you have a 1/4. Okay, we have a 1/4 of the fractional of the 2 power of k design. So this one we will write as the 2 power of k minus by 2. Okay, so we only run quarter of them only. Okay, so the 2 power of k minus 2 design may be constructed by writing down a basic design consisting of the run associated with the full factorial design in the k minus 2 factor. If you still remember just now, if you consider the case of the k minus 1, then I have introduced for you what is a basic design. So now we go for the 1/4. So therefore, we have a 2 of them is missing. I mean the 2 factors you can be list down later. So you write down only for basic design only for the k minus 2 factors. Then another 2 columns or the 2 additional columns with an appropriate chosen iteration will involve the first k minus 2 factors. Okay. So because you are considering the 1/4, therefore you have a 2 another 2 factor will be you need to considering what is the generator you consider. After that, you can get the factor, the remaining of the 2 factors. Then we can get the plus minus sign here. Okay. So under the 2 power of the k minus 2 fractional design, means that is a 1/4 fractional design. You need to have the 2 generator here. Okay. So under the 1/4 fractional of the 2 power k have the 2 generator. So you need to select 2 generator. Then from these 2 generator, we can form the 2 generating relations. So it's a I is equal to P and then I is equal to Q. Okay. So you have this one is before that you only have 1 of them. Now you have 2. Okay. So because of, if you recall back for the 1/2, you can have a P is either you run for the positive side or you run for the negative side. So similarly for the 1/4 fractional, you also can have a plus minus P, you have a plus minus of the Q. So therefore, under the 1/4, 1/4 of them, you can have a minus sign, you can have a minus plus, you can have a plus minus, you can have a plus plus. So here will be the 4 of them. So you only run 1/4 of them. Either you run the first one, or the second one, or the third one, or the fourth one. Okay, so this one is why you run the 1/4 here. So the fraction with all the P and Q positive is called the principal fraction. So this one is referred to the principal fraction. Okay, it's referred to the principal fraction here. Okay, so under the 1/4 fraction design, your complete the complete defining relation is no longer 2 separately. Then our complete defining relation will be given by the I is equal to P equal to Q, then equal to the iteration of these two, or the product of these two is a PQ. So our defining relation will be consist of the PQ and the PQ. Okay. So the alias of any factors produced by the multiplication of the columns for the effect by each words in the defining relation. Okay. So if you want to obtain the alias structure of this thing, what you need to get is just a complete defining relation, and then you multiply by the factor of the each one. Then you will get what is your alias structure for the rest of them. The word will be similar one, but now your complete defining relation will consist of I equal to P, Q, and equal to PQ. Okay. So clearly, the effects have 3 aliases because your I is equal to A, B, Q, and the PQ. They consist of the 3 aliases. So should be careful in choosing the generator so that potentially important effects are not aliased with each other. Okay, so this one is when you list out the alias structure, then you can observe it. We do not want to have the main effect will be iterate with the main effect. Okay, because if you have a main effect will be alias with the main effect, then you do not know the contribution is either come from the main effect for the A or main effect for the B. Okay, so therefore your generator, you must choose it carefully. This one will different from the generator of the previous case. In your previous case, your generator, if you only consider the 1/2, normally we will choose the higher order iteration as the generator, but under the 1/4, you may not be choose this one. Okay. So I show you the example of here. So if let's say I have a 6 factors here. Okay, we have a 2 power of 6 minus 2 design, means that this one is a 1/4. So for example, if I choose the I is equal to ABC, D, I is equal to I choose this one first. Okay, I just choose the ABCE. Let's say for example, the I is equal to ABCE because it's a -2. So if the I equal to ABCE, so of course we want to know the factor of the E here. The E can be equal to the here you multiply, you will get is a ABCE. So it's E square. So therefore you get the E is equal to ABC. Huh? Just now, if you still remember, I mentioned that it's a 2 power 6 minus by 2. So you write the basic design is only for this one, ABCD, as the basic design of the plus minus sign. For the E here, you can choose the following defining relation. Then you can get the E is actually the ABC. Okay. Then another one, you can choose the I because you want to get the F here. You can choose the 4 one is maybe the B, C, D, F. Okay. So from here you get the F times the I will equal to B, C, D, F times the F here. Okay, you times the F on the left hand side, you times F here. So therefore you get the F will equal to the B, C, D. So from here you write the basic design of this thing, then you can get your E, you can get your F. So therefore, you can complete the plus minus sign, and then at the same time, you know what are the treatment combination should be run. Okay. So under this one, what we can say that if we want to say that the design generator of this one, okay, the design generator will be equal to the ABCE and the BCDF as a generator of here. So therefore, we can get the E will be equal to we can get the E will equal to the ABC. And then we have a F will equal to the BCD of here. Okay. And then just now, if you still remember what I mentioned here, if you have a P is your generator, the Q is a generator, then the product of these two also is a generator. Therefore, under this case, under here the iteration, so we have just now is A, B, C, E as the one of them, the generator of here. We have another one will be the B, C, D, F. So we consider their iteration. So we have A, B, C, E, then multiply by B, C, D, F. Okay, if you multiply all these things, then you can observe that the A, D, E, F is their iteration of these two protein. Okay, so therefore we have a first one, we have a second one, we have a third one. Okay, so they are complete. They are complete. A complete defining relation of all these things will be the first one will I will equal to the A, B, C, E. The first one. You have a second one, I will equal to the B, C, D, F, as you mentioned here. The third one, I will equal to the last one is A, D, E, F. Okay, so these three are the defining relation of here. Okay, so after that, we can be list down all the alliance structure instead of writing in the separately. We can get the I will equal to the A, B, C, E. So this one is what you have for the case of the 2 power of 6 minus 2 design. The alliance structure of the 2 power of 6 minus 2 design. Okay, so from here we can get the alliance structure will out. Means that we multiply by A here, we will get is a B, C, E will equal to the A, B, C, D, F. Then it will equal to the D, E, F. So this one is one of the example for the alliance structure. Of course, you can list down all the rest of them. Okay, so this one will be very important to tell you that what are the restoration. Of course, you can still list out all the B. You can list out all the B. You can list out all the two-factor iteration and so on. Then you can observe that this one is actually the restoration of the. In fact, it's just a restoration of the 4. Okay. Okay, so this one is here I think that I do the typing wrong. This one should be the 2 because we still under the 2. It's a restoration of the 4. Okay, you can be list down all the alliance structure, then you can check whether this one is a restoration 4 or no. Okay, so this one is where we run the principle. What I mean the principle parts is means that both of them are positive, so this one is called the principal fraction. Because this one, they consist of the 1 quarter, so they can have both of them negative, one negative, one plus, one positive, one negative, and both of them is plus. So therefore, over here, I say that there are 3 alternate fractions of this particular 2 power of 6 minus 2 design. Okay, so that one will be the, if you want to consider, there will be the A, B, C, E. Okay, it's similar to here. And then another one will be I will equal to the negative B, C, D, F. Okay, or you can have another one will be the here will be equal to the negative A, B, C, E. I will equal to the B, C, D, F. Okay, this one is a 1 positive, 1 negative. This one is 1 negative, 1 positive, and then both of them is negative. Both of them negative. Okay, so you run the 1 quarter, you have 4 possible cases. One of them is a plus plus, this one is a plus minus or minus plus or plus minus minus. Okay, so you only run 1 quarter of them. Okay, if you have a 2 power 6 factorial design, the full factorial design, you run all of them, you will get the 2 power 6, you get the 64 treatment combination. But now what you need to run is only 1 quarter of them. So you divide it by 4, you only run the 16 treatment combination. You only run 16 of them. Either you run the first one, the principal fraction, or you run the second one, third one, or the fourth one. Okay, so we expect that if we can run just the fraction of them, we can be identified the important factor if possible. Okay, so this one is a following example in the example 8.4 here. So this example will be consist of the 6 factors. Okay, they have a 6 factor here. So just now, if you still remember, I have a basic design. I will write it as a ABCD, and then for the D and the E here, I can base on the I, the defining relation, to get the what is the plus minus sign of the E and the F here. Okay, so this one is the diagram of here, where the ABCD you write as a plus minus sign, similar to just now I have mentioned. So for the here, the E one, okay, the E here, the E will be equal to the ABC. So means that in this example, they consider the generator of them. Okay, the first generator they consider in this case will be the A, B, C, E. Okay, of course you can choose other generator. The second generator they consider in this example will be the B, C, D, F. Okay, they consider these two is a generator. Then from these two generator, they multiply by they have a I will equal to A, B, C, E. So you multiply by the E here, they get the ABC. So this one will equal to what you have here. Similarly, for this part also, you have a second one. So here are all the treatment combination of here. You no need to list down all the 64, all the treatment combination, and then you consider which are the treatment combination you plan to run. Okay, by using the following one, then you need to list down only those of the treatment combination under the principal fraction, because I consider the plus sign and the plus here. Okay, so the experiment they will run it under the following treatment combination. This is the result they observe. Okay, the second one they run at the A at the height level, E also at the height level, where they give the notation as a AE. The result of the experiment they run is a 10, and so on. They complete all the 16 treatment combination. So based on this 16 treatment combination, are we able to identify which factor are important factors? And then under each factor, which level you need to consider, either the lower level or the upper level, or the low level or high level. Okay, so we only run the one quarter of them. Okay, so after we get this, after we get all these things, of course we can be list down all the alliance structure first. Okay, so I just list down here is the I will equal to the, you have a first one will equal to the here A, B, C, E will equal to the B, C, D, F. Okay, will be equal to, if you multiply by these two, the iteration, the B and C will cancel off. You will get is a B and C will cancel off. You have a D, E, F. So this one is a complete defining relation of here. So of course you can be list out all the alliance structure. The A will equal to the BCE will equal to the A. Okay, you can list out all the main effect. Of course, you also can list out the BC. You multiply BC, you get the AE. Multiply BC, you get D. Okay, so you still can list down all of them. Okay, so all these things will be all the cases you have. Okay. You can list out all the possible restoration of this thing. Okay, so as you observe it here, just now I write the BC here. So it's one of the example is here. Okay, you can see BC, AE, and the DF to the BC with the AE and the DF, and then plus the the 6-factor iteration. So you can observe this thing. It will appear here. It's appear over here. Of here. So similarly for the A here, the factor of the A here, the A will be here is with the 3-factor and 4-factor iteration. So we just list out only the A here. Okay, why we only list out this thing? We can be assumed that all the 3-factor onward we can be negligible. All the 3-factor iteration and the higher order is negligible. So means that if the factor of the effect of the A you are calculating itself. These 3 we can be ignore it. This one also we can be negligible it. So in fact you're calculating a BC, AE, and the DF. Okay. So therefore they just write down in the 3 of them only. The rest of them they will ignore it. Okay. So if you observe the diagram of here, if you observe the effects of here, the regression is later on. If we observe the effects out of here of them, okay, we can see that this one is quite large. This one also quite large. This one also is considered as a large value. This one is a 5. We are not very sure. But if we treat it as a large also, okay, we don't not very sure. But these are a few of them is considered as quite large. We also can observe the sum of square. This one is really very large. So it seems that the factor B is quite important. And then the factor A here also is important because the sum of square is quite large here. Similarly, you have a AB and CE is considered very large. This one is a 115 also. We may not be known, but we can be consider it. Then we can consider it. Okay. So to be confirm it, then we not only view the values, we plot the normal probability plots. So based on the normal probability plots here, they only identify the A, AB, and the B are important. So means that just now we guess for the 4 point something also not really very important here. So they only identify the factor A, factor B, and the factor of the AB. AB will be here. So these are the 3 important only. These are the 3 is important. Okay. So the factor, if you consider the main effect here, the C, D, E, F, they are not very important here. So we can be think that these are the not important factor. So for the A and the B here, they are the very important factor. But because of the A and the B here, they consist of the layer structure like this thing. We only can do is we assume that all the 3 factor and the higher order iteration are negligible, then their main contribution come from the B. Similarly, for this part, AB and the CE, if you have a AB and the CE here, if you observe that this part is if you multiply all these things, you have a AB will equal to the CE will equal to, you multiply AB, you get the A, C, D, F. You have another one will equal to A multiply, you have a B, D, E, F. So these 2 will be actually, if you negligible about all these things you will cancel off it. All the 3 factor onward you have it, then you are estimating the AE plus the CE. But from here, from this analysis, I'm using the same interpretation because the factor C and the E are not significant. So the CE iteration, we can think that they have a very small contribution. So therefore, from this analysis of running the 1 quarter factorial design, we are identify it out the factor A factor B, and the iteration of the AB are important. So means that all these three will be help us to formulate the regression model, where we're going to do some prediction or we try to estimate what are the response value. Okay. So from this analysis, we can be identified A, B, and the AB are important. Of course, we need to do some assumption as I just now mentioned. So because the AB iteration are significant, if you want to get the higher value, so of course the factor A, you should be choose the high value, and then the level of the B also you choose the high value. Okay, so this one is regarding the 2 power of 6 minus 2 fractional factorial design, or you run is a 1/4. Okay. Okay. So in general, you can be run is a you can run is a 2 power of k minus by p fractional factorial design. Of course, your factor must be very large. You have a, let's say, 6 factor or 7 factor. You have a many factors, then we can run only the portion of the treatment combination. So that they run is a 2 power of k minus by p here. So the 2 power of k fractional factorial design contain of the 2 power of k minus p runs is called the 1/2 power of p fraction of the 2 power of k design. Okay, you can think about it. If the p is equal to 1, you only run the 1/2. So is this one will be equal to the 1/2 power of 1 is equal to half. You only run the half of the fraction of 2 power k. For the case of the p is equal to 2, you have a 1/4. Okay, it's a 1/2 power 2 is equal to 1/4. You only run the quarter of the 2 power k design. Okay. So in the general the fractional factorial design, you consist of the p generator. Okay, you consist of the p generator. Of course, you also, when you consider their alias structure, you also need to consider their iteration of all these generators. So each effect has the 2 power of p minus 1 aliases. Okay, so they consist of how many aliases? Is actually the 2 power of p minus 1 aliases. So if you still recall back, you have the 1/2. So the p is equal to the 1. So it's a 2 power 1 minus 1. You have a 1 alias. So means that you have a first one will equal to the second one if you run for 1/2 when for the p is equal to 1. For the case of the p equal to 2, you can have the first one equal to the second one equal to the third one. Okay, you have 3 of them. If you still remember, okay, so the p equal to 2 is a 2 power 2 is 4 minus 1. You have a 3 aliases. So this one is what they mentioned here. A were aliases with 3. So this one is what they have 1, 2, 3. Okay. Okay. So for the large k is means that your the fraction of them, the k will be the factors of them. Higher order iteration is to be negligible. Okay, of course, those are the high order iteration. If you consider them as the important, then the whole design you can't interpret it very nicely. Okay, so therefore, those of the high order iteration normally we try to ignore it unless you have enough information to maintain it. Okay, in your model. Otherwise, for the high order iteration, most of the time we need to give up because we already run 1/2 or the 1/4 of the fractional design. So we need to give out certain information. Okay. The following one is also another criteria. It is important to select the P generator for a 2 power of k minus p fractional design in the such way that we obtain the best possible alliance relationship. Okay, so this one is what they call as a best relationship. It means that we don't want to have the main effect will be alliance with another two-factor iteration, or the main effect with the three-factor iteration is possible, but two-factor iteration we try to avoid it. Okay, so how we want to avoid it? Of course, one of them is choose the highest possible restoration. If you check it out, if you have a restoration 3, then the main effect will iterate with the two-factor iteration. If you choose the restoration 4, and then you have to choose a restoration 5. So we will choose the highest possible restoration. Okay. So how we want to interpret as a higher the highest possible restoration? You need to read through the definition of what is the restoration 3, 4, and 5 here. Okay, and then you need to choose your generator carefully. So I will give you the following example of here. You can observe it. This one is one of the possible choices of here. In this example here, you can observe it. There are 3 choices of the generator because you have many possible generator. So what are the generator you should be considered for the 2 power of 7 minus 4 design for the restoration number 4? So all these things will be lead you to the same. Okay. So over here, you can observe it. If the design one, I choose a generator, the F is equal to ABC, the G is equal to BCD. So because this one is run the 1/2, so therefore you have a 3 alliance structure here. You have a I is equal to ABCEF and so on. So we have another generator. We don't want to use the BCD. We use the ADE. So we will end up with the I is equal to ABCF and so on. So this one is the second generator we consider. This one is the third one. If we consider the F is equal to ABCD and the G is equal to ABDE, then we multiply out. These are the alliance structure we obtain. Okay, so you can be check it out over here. The alliance structures, the two-factor iteration, these two will be the two-factor iteration will iterate to each other. Okay, if you observe here, you observe up to here, the I is equal to ABCF, and the BCDG and so on. You can observe that. Let's say I multiply by the A will equal to the BCF will equal to the A, B, C, D, G will equal to the, here is a D, F, G. Okay, so the main effect, it do not interact with the two-factor iteration. Okay, but the two-factor iteration will interact with each other. So this one is those of the here, the restoration of the 4 under this case. Similarly, for this thing, we multiply all the two-factor multiply together, then you can observe that AB is equal to the CF. Of course, in this example here, or in most of the example here, we will consider the 3 to 4 orders higher to be negligible. Okay, so what we obtain will be here. Okay, the first one, the second one, and the third one. So based on these 3 design here, which one we want to choose? Okay, if you choose the first one, okay, if you choose the first one, if your AB and the CF or the AB here, the effect is significant, then you do not know the effect is come from the AB or the CF. Okay, because these both of them together. So over here, you consist of the 1, 2, 3, 4, 5, 6, 7, 7 of them. Okay, the 7 of the two-factor iteration. Okay, but for this one, they only consist of the 1, 2, 3, 4, 5, 6, 6 of them. But for this one, they consist of the 3 of them only. Okay, so in our analysis here, we will always choose those of them with the less alias structure of here, because the two-factor iteration in our case will be very important. Okay, so in the following one, I will just list it down. You can observe it here. This one is a 4, this one is a 4, this one is a 4. So I will write it out, the words here, as a 4, 4, 4 here. They consist of the 4 digit, 4 letters, 4 letters, 4 letters. Where else for this thing, we consist of the 4, 4 and the 2, 4, 6, 4, 4, 6. So we have a 4, 4, 6. For this one, we have a 5, 5, 4. Okay, we have a 5 here, we have a 5 here, we have a 4 here. Okay, so of course, we will choose those of them based on this diagram here. We will choose those of them is a less aliasing. Okay, for the two-factor iteration. In fact, we are not only concentrate on two-factor iteration, because as I mentioned, three-factor and the higher order we can be negligible. For the main effect, of course, you can observe it. A will iterate with all these things, or the alias structure. All these things will cancel it out. For the main effect, we will directly can be calculate the effect from the A. But for the two-factor iteration here, you have so many of them. This one will be less. This one will be the less aliasing. Okay, so I can say that this one will be the less. They have a less aliasing. So in the following example here, even though both 3 of them, they give you the same restoration of 4, but we will choose this one as our generator, and then we run the treatment combination, will run under this part of the treatment combination. Okay, we are using the following one to run the treatment combination instead of this one or this one. Okay, so here will we tell you that sometimes restoration alone is insufficient to distinguish between the design, because as you can observe it, all these things is a restoration. Okay, they can have design A, design B, and design C, where they're using the different generator. So you cannot just based on the restoration, then you will tell that, oh, which one I would need to use. Because instead of the restoration, we also want, if possible, the two-factor iteration will have a less aliasing. Okay, this one is the first point. The design C is minimum the number of words in the defining relationship that are the minimum length of here. Okay, because of, as you can see from here, they only have 3 of them, whereas for this one, you have more than that. Okay, you have here, and then this one have more. So here will be tell you that the number of words here, because if you have a 5 here, then of course we want to choose the higher restoration will better. Okay, so this one will say that design C will minimize the number of words in the defining relation on the minimum length, the minimal abbreviation design. Okay, so this one is you can observe from here. So we will choose this one is our generator to generate. After that, we consider this following case. So this one is one of the here is a design here. Okay, so just now the previous example we consider we have 7 factors there. Okay, if you observe it here, you have 7 factors. This one is a 7 factor. Then you minus by 2. You run for the quarter of them. So you consider here. If you consider the 7 factors, you run the 7 minus by 2 here. Okay, you have a 7 factor, you just run the 1 quarter. So the suggested one, it should be this one and this one. Okay, so here it show you that what they have here with the possible one. This one is just now in the here. We use the ABCD and the ABDE. Okay, this table will show you the best combination if you want to run for the 7 factors with the quarter. So the restoration 4 you choose for the following one as your generator. Okay, but if you observe it here, you have a different combination, but this one is the best. Okay, means that they have a less aliasing. Okay, so of course we have other factors. You can be observe it. If you run the experiment, you need the many factors. How many combination you need to run? Okay, so we can have 6 factors. You only run the 6 minus 1, 1/2. So you run only 32 treatment combination. If you want to run the 1/4, so you only run 16 of the treatment combination. If you want to run furthermore 6 minus 3, then you only run the 8 treatment combination. Okay, but the restoration under this case will be less. Of course, when you run a treatment combination become less, though you want to make the conclusion is you can have a difficulty. Okay, maybe you not enough. So therefore, if you run the 8 of them, you still cannot make the conclusion, then you still need to run another 8 of them so that they become the 1/4 here. Okay, because you run the 6 minus 3 is only 8 treatment combination. They're not enough, then you need to run some more, another set of them so that you can make the conclusion to identify which are the important factor. Okay. So under the fractional design, we cannot say fractional design can help us save a lot of time. But the problem is instead of saving the time, saving the cost, you also need to check out whether the result obtained can lead you to make the conclusion. If you cannot make the conclusion, you still need to run more treatment combination. Okay, so this one it should be the last one for the fractional design. Okay, this one is the last page for the fractional design here. Okay, so far the first one from the beginning of the what you have studied before I go to the regression here, the first one is what you have learned before is just a one-way ANOVA. Okay, so you have a single factor. Okay, you already know what is a single factor model they look like. Then if extend it to the second one, we have a factorial design. Also using the ANOVA techniques, so you have a more than 2 factors. You have more than 2 factors, then some more you consider their iteration. Okay, then after that I go through with you. Is another one is a 2 power of k factorial design. It's a subset of the factorial design. You only concentrate on the 2 levels, but they still have a more than 12 factors. Okay, so these are the 3 designs what we are considering here. After that, for this section, we will run is what they call as a fractional design. Okay, so this one will be the last chapter of the fractional design under here. So we have a 2 power of k fractional design. Of course, all these things is only concentrate on the main factors, but you have another one is called the Nelson factors. Okay, you have a Nelson factors, or I just write the block design. Don't want to. Okay, you have a blocking here. So for each one of them, for the one-way ANOVA, for the factorial design, for the 2 power of k factorial design, for the fractional here, in fact, you also can have blocking, the blocking here, or they call the block design here. Okay, blocking is a technique, then you have a block design. Okay, means that you have a Nelson factors to be considered. So therefore, you need to eliminate out or to take out the Nelson factor from the calculation of the sum of square for the error. Then this one will be the block design of here. Okay, of course, under the block design, you also learn the technique is called the confounding techniques. Okay, so these are the things here. The next one we will go through will be the response. We will go through will be the response surface methodology. So they were related to the 2 power of k factorial design. Okay, they were related to the 2 power of k factorial design. Okay, they were related to this one. Okay, but of course, before you learn the response surface methodology, I will introduce for you what is called the regression analysis. Okay, I just go through touch and go only for regression analysis because the regression analysis is not the main topic for this our study. Because we want to formulate the regression model, then we need to somehow need to know how the regression analysis get it, so that you can formulate the equation. So after you know the idea, we are not necessary we need to use the equation. We can be relate the 2 power k factorial design with their effects. Actually, the idea is come from the effects. Okay, so this one is here. We will go through this part. We will go through the regression coefficient of this part. Okay, for the 2 power k factorial design, even though the fractional also we can do that. Okay. So this one will be lead you to this section. Okay, so I think we stop for the while, then we continue later. Okay, we continue later for this part. This part is just an introduction. I only have 10 pages. Okay. Okay.